Well, good morning and welcome to day two of TechCon 2025. Appreciate you joining us again today. And if this is your first time, I'm Ray Daniel. I'm responsible for the integration portfolio in the Americas. And so we had a great day yesterday and looking forward to another one today. Just to keep in mind, if you have questions, uh, post them in the chat, and we have someone monitoring them, and we'll get you an answer as quickly as possible. And in addition, at the end of the day, we have office hours, and we had a very active office hour yesterday. We had, I think, 26 people on the call, and anybody is welcome to voice a question and have our speakers from the day jump into those questions. So keep that in mind. So, a few years ago, we started talking about MQ and containers, and we were all kind of scratching our head a little bit about that in the sense that most MQ workloads are what we call persistent, and the notion of just basically shooting a container in the head and starting up another one kind of sent a chill up our spine, and so it was like, how's this all going to work? Well, guys like Jonathan Rumsey out of our Hersley lab have been working on this for some time now, and they've got a lot of technology that they've built that really answers that question. So with that introduction, John, I'm going to step out and turn it over to you.
Thank you, Ray, and good morning, everyone, and good afternoon. With me today, I've got my colleague Ian Edwards. He is going to be available to answer some of the questions that come up on the chat. But without further ado, let's dive into talk around resiliency options for MQ and containers. So, unfortunately, technology, whilst we rely on it, it isn't always working all of the time. Only last week, I was just saying to Ray before we went online that the weather here in the UK is still very cold. And last week, my hot water central heating pump broke down. You kind of just expect it to work, and when it really doesn't work, it can have big consequences. Yeah, Mrs. Rumsey wasn't very happy that there wasn't any hot water for showers, washing. So whilst we expect technology to work, it cannot just be expected to work 100% of the time. So even unexpected failures, as well as those, there might be some reason why you need to take down your messaging solution to provide maintenance. It's very important to make sure you're up to date with security fixes. Resiliency, whilst I'm going to focus on availability today, isn't just about whether your application can continue working, isn't just about whether your messages are available. It is around things like security as well, hardening, making sure that you're resistant to issues as they arise. So a messaging system that is architected to provide redundancy, to be fault tolerant, will be in a much better position to handle availability events. I wish my central heating system had two pumps rather than just the one. We'll go on to look at about what happens when your availability options fail. Do you provide a backup to your backup? Where do you stop? And we'll look at some of the options that are available and how you combine these with various different options in the product, and how you can work with your application development team to make sure your applications are resilient, to make sure your messaging backbone is resilient, and to make sure your messages, if they're critically important to your business, if they are time critical, what options are available and how can you reduce that availability time if you were to need to drop one of your instances. Okay, so we do have a poll question here. So this is MQ resilient if an application can connect to a queue manager 100% of the time? So if you have a queue manager available 100% of the time, is your MQ system resilient? So there are a few kind of answers here. Is yes, yeah, of course it's resilient if my application can connect to my key manager 100% of the time. No, and it depends. So we'll allow a few seconds for the poll to complete. So really there is a trick question, really. So it's going to depend on your applications. So if an application is able to connect to a messaging service, and provided they don't care around how quickly messages are processed, then it may be that that is a resilient system. If your applications have time critical messages and you were to lose a key manager, but you still had another key manager that could process your workload. So if you had greater service availability, you had 100% availability of your messaging service, it's the availability of your message that's critically important for that application. And even more so, whilst one of your applications may be available, if you don't have sufficient responding applications, if you have one requesting application, then you have 1,000 requesting applications. Do you have sufficient capacity in your responding applications to be able to handle the workload? So there are lots of different factors which can be important in determining whether a system should be considered to be resilient. I kind of break this down into 3 layers. Of course, one of the most important things is whether your application is running. If your application isn't running, it really doesn't matter whether your messaging service is running. You're not having anything put your messages into the service or to remove them. And lastly, as we kind of briefly touched on, is the message. So whilst a particular instance of a service may be available, if you have a instance of a service go down and messages are, as the MQ, the queue part, are on a queue, you are then reliant on that instance of the service coming back up and making that message available again. So all 3 of these are critically important. So whilst it may be very easy to think about, okay, I need to make MQ highly available, I need to look at what options there are at making the service highly available and the message highly available. These are 2 common areas, so we'll look at a couple of those. Actually, it's really important that all 3 of these worry about how they deal with faults, how they deal with what happens if the service isn't there, what happens when the message isn't available for my application to consume. So we'll look at these in kind of a bit more detail. If an application isn't running or doesn't handle breaking connectivity, then it doesn't matter how reliable the rest of the system is, you're not going to have messages being exchanged between your applications. So resiliency really starts and ends with your application. So that's really, really critically important. The service is kind of saying, if a queue manager provides application with a messaging service, if that's a suitable service, then your messaging service is available. But as we see, certain types of applications may have an affinity to say, I need to make sure that I either connect back to a particular service again and again, time after time, to make sure I only talk to that one queue manager, or indeed that I have messages which have a shelf life. So if I have some sort of piece of information that's only valid for a few seconds, I really can't afford for that queue manager to go down for a minute, because all the messages queued up on that queue manager, and now when it comes back up, whilst MQ will retain them and provide that excellent persistent message availability and transactionality, those messages are no longer valuable to my business. So we'll look at those in a bit more detail. So the first couple of areas I'm going to cover around application service availability are more generally applicable to MQ. The message availability options I'm going to dig into are going to be very specific to containers, very applicable to running in that environment. But we'll look at a kind of diagram which kind of shows how all 3 of these play together. So imagine I have a single queue manager and I have a producing application here on the left and a consuming application there on the right. Whilst that queue manager is available and those 2 applications are available, that's great. My messages can go through that queue manager. If the consuming application isn't available, the queue manager can hold on to those messages until it does become available. I can add greater service availability by adding multiple queue managers. Every time I provide a different location which applications can connect to, I've increased my service availability. I'm not reliant just on that one queue manager. If that one queue manager were to be down, I have other queue managers that could handle that application traffic, provided the application is written in such a way that it doesn't have that tight coupling to a particular queue manager. So to highlight message availability, we'll imagine what happens if I send the message to the queue manager. Both applications may or may not be running at this point, but that queue manager goes down. Now, if this message has, again, a shelf life or a kind of a limited period of which time that it's valuable to your business, then you have potentially an issue. You want that message to become available again so that consuming application can get on and process it. So in applications that require high message availability, we're generally talking about the recovery time it takes for a queue manager that has either gone down for a planned maintenance or for an unplanned outage to get back and running again quickly with all the persistent data that MQ is holding on to. Okay, so let's roll back a bit and talk a bit around the application availability. As I said, availability and resiliency, in my opinion, really starts and ends with your applications. That's the point at which your messages become messages and when they cease to become messages. So your applications are your start and your end point at which a message becomes something that is carried around by MQ. So you need to really consider what sort of capabilities and requirements your application requires. Do you need to have sufficient consuming applications, for example? So if you just have one producing application, is one consuming application going to be fine? Yeah, that probably does make sense. But if you have thousands of producing applications, if they all have the ability to connect and maybe the start of a business day, then if those messages have limited validity, then you're going to maybe want to have much more consuming applications and maybe trigger more to start with those sudden increases in activity. Now, applications that use local bindings connections to queue managers will undoubtedly outperform an equivalent application that's been linked to run as a client. And this is just because you're talking over shared memory or over a local socket rather than over a network. But those locally bound applications are tightly coupled to local queue managers, and so those may struggle more to deal with a change in availability. If your local queue manager ends, then unlike a client, you have limited connectivity to be able to connect to an alternative messaging service. And so there are lots of capabilities that MQ builds in to help out with that, with your application availability, things like auto reconnect, client channel definition tables, and we can work with things like network sprayers and load balancers to make sure that your applications that can have a decoupled approach can connect to an alternate messaging service. So 3 things I think that it's important for all applications that want to be highly resilient should do. One, of course, is to expect failure, not just when they try to connect to the queue manager, is the queue manager running now, but in fact on any interaction with the queue manager. So puts, gets, opens, anything that could have any interaction with MQ, always expect it could fail. If a queue manager unexpectedly fails, you'll get a connection broken. How does your application deal with that? What sort of logic would it need to go through? A very simple logic, you may be able to use the auto reconnect, but anything more sophisticated, you may need to deal with that in your application. One thing that can help deal with that, with the connection could break at any point, as we said, things fail all the time, you may not be in control of when that happens, is transactions. So MQ provides on put and gets this sync point option. So the sync point says, I want to get to the end of my transaction, I want to issue a commit, and when the commit comes back to me successfully, I want to then get that guarantee that everything in that transaction has worked. If it hasn't, then I want everything to roll back and I want to start again. So really, really critically important for any applications that want to know what's happened to messages is to use sync point. So I'll give you another example. If you have an application that's wanting to get a message from a queue, it's wanting to get a persistent message, it goes to get that message and then you get the connection break. Well, did that message get removed from the queue? Did it get sent on the network? Did it then fail to get delivered to the application? A sync point would effectively save your bacon here. It would roll everything back, so the get will be dependent on the commit happening, and you'll be able to then roll back and then get that message again. So sync points are really important. You know, even if you're saying I want to put persistent message, transactions are really critically important to make sure you know what's happened and what hasn't. Lastly, decoupling. I've touched on this a couple of times, but applications that are a little more freer to say, I want to be able to connect to the messaging service, and I don't necessarily care that I have message sequencing requirements, or I don't really care that last time I spoke to this queue manager, if there's another queue manager that can handle my workload this time, I'm happy to connect somewhere else. And this kind of then combines with some of the other features of MQ, things like uniform clusters. A decoupled application is much more flexible to be able to deal with the fact that your preferred location, the place where you would normally connect to, and your queue manager that normally deals with your work isn't available right now, but you could go to an alternative. So decoupled applications really do offer the best in resiliency. So now we'll talk a bit more about service availability, and this is really about dealing with, again, you know, if my preferred location isn't available, is there somewhere else I can talk to? And this is a lot of customers will talk to me and say, you know, can I do this in an active topology? And so it kind of depends what you're talking about. So MQ on distributed and containers does offer active service availability. You can do that. You've been able to do that for many years, even without clustering, to have two queue managers where your applications will be able to connect to, that have the same set of queues, that have the same set of applications that handle the requests that go to that queue manager, offers this active topology. You know, they don't need to be the same queue manager. When it comes to talking around message availability, we don't have that support on distributed or container platforms. Now there is, you know, the ZOS guys are going to kind of hold my feet to the fire here. There is something called shared queue on the ZOS platform, which does offer this active topology where two queue managers will share effectively the same queue data between them. That depends on the coupling facility, is very tightly coupled to hardware support. That isn't available for distributed or container platforms. So active for service availability, absolutely yes. For message availability, that isn't available on containers or for distributed platforms. MQ clusters, we'll come on to talk about those again in a bit more detail. This can help group together a set of queue managers that offer similar services, or indeed in a uniform cluster, specialized form of MQ cluster. These can tie together queue managers that all offer the same service, and they will also be able to handle horizontal scaling. So if you have the need to increase your service availability, adding extra members of that cluster can very quickly allow you to scale out. And all, again, with the reconnect options, allow you to reconnect your applications to balance that workload. So if you have three queue managers in a group today and you needed extra capacity, adding a fourth one, and in a uniform cluster, that would be able to handle spreading existing connections over the four queue managers that could handle that that messaging requirement. So as I said, we've covered some of the options there for active service availability. You know, the very simplest is I have two queue managers, ideally more, that offer the same set of queues. That gives you a very simple active topology. But if you're just having two queue managers like that, having something that deals with horizontal scaling, or if you have one of those queue managers go down, what do you then have to rebalance them to be able to connect over to the remaining availability? And then how do you then balance them back once both queue managers are running? So that's when you have something like uniform clusters or MQ clusters that will be able to handle that. Lastly, we're going to talk about message availability. So message availability really is about a message that has been given to MQ. We've stored it on a queue, it's point to point, and we're waiting for the consumer to be able to come along and collect that. That may be because that consumer is busy, or it may not be connected to the queue manager at the time that the message has been produced. Now, with message availability, as I've said before, it's generally a time critical thing where you would say, I need a message to be processed within a certain period of time. Some applications will have that requirement, others will not. So it's absolutely perfectly fine for you to have a queue manager that says, I need to have this type of message availability, and for another application to have a different set of requirements, and for you to have two different solutions for that. So there is no one size fits all. Message availability, again, is generally tied to the requirements of applications as to whether you need those messages which are held on the queues to be made available very, very quickly. So we'll come on to see this again, hopefully later in the demo with native HA of how you can really reduce the time that those messages are unavailable for both planned and unplanned failures. So now we're really going to start focusing on MQ and containers and the message availability options that you do have. The first is a single resilient queue manager, and as the name suggests, this is just a single instance of a queue manager, single copy of the queue manager data. Some of the other resources around it may themselves be resilient, so your storage layer may be resilient, but really you just have a single copy of the queue manager, and we come to see that the message availability is tied directly to your service availability. If your service is down, your message is unavailable for the same duration too. You also have the option of multi-instance. So multi-instance queue managers predates containers, but you can do it in containers as well. And this is where you have effectively shared storage. That storage is connected to by two instances. The first, which is started, becomes the active, works just like a single resilient queue manager. The second becomes the standby. So the standby watches and waits file system locks on that shared storage to be released. So whether that's a planned failover or an unexpected failure. And should those locks get released by the active, the standby is there ready and waiting to very quickly take over. So that can reduce the recovery times, and we come to see how those recovery times really have a very big impact on how quickly your message availability can recover. And lastly, we come to talk about native HA, which is, as Ray said earlier, is something that my team have been working on. And this is where we've gone for something which is much more around a shared nothing approach. So we have 3 replica copies of MQ data, and we ensure that these are maintained consistently using the raft algorithm. Now, what this provides us with is a HA solution, so it allows you to very, very quickly with the raft capabilities, be able to detect that you've lost an active instance, and very quickly one of your replicas can then jump in and take over. And again, that gives you the ability for the messages which have been committed back to an application to say, yes, this message has landed on a queue, for you then to make those messages available for consumption. We'll also come on to see how some of the container technology we offer, things like the MQ operator, will also understand the relationship between these replica copies and how they can best manage planned failovers. So, for example, if you wanted to roll out maintenance, you can use the MQ operator to really minimize the downtime that you have for your applications. And then, yeah, as I said, the very last thing that we do today is we'll go through a demo which will cover native HA and some of the newer features that can be used for a DR solution, the cross-region replication, which has recently gone out in MQ942. So I'm not going to dwell on this too much around the single resilient queue manager, but as I said, it will really depend on your application. A single resilient queue manager may be absolutely perfectly fine for many applications. If your application doesn't have this time critical nature, that messages it may be fine for them to be processed maybe a few minutes or a few hours or even a few days later, then a single resilient queue manager will give you that message availability if that's what you need. If you need those messages to be very quickly processed, if you have trades or you have requests, orders that customers are going to be very unhappy if their order doesn't go through today and doesn't get processed tomorrow, those sorts of things, you probably do want to think about how you can improve on the single resilient availability. We'll look at how this kind of plays into the service and message availability and how that compares between these options shortly. Multi-instance is an improvement on that single resilient queue manager in that you're not just relying on Kubernetes to spot that your container has failed, but the multi-instance will have this second instance ready and watching the shared storage to make sure that there's an active running all the time. So the standby is just watching and polling, waiting for that active to fail, and that gives you a much shorter recovery time than the single resilient queue manager. And again, a lot of this will also depend on your other components in here. So if your storage itself isn't that available, if you're having your shared file system have resiliency problems of its own, that is going to have an impact on the queue manager. So having a kind of reliance on the storage layer and having the kind of that tie to one particular layer means that your availability and resiliency may suffer if the availability of your storage layer isn't as good as the rest of your stack. Native HA, as I said, we aren't talking about a single storage layer here. Each instance has shared nothing. So each instance has its own pod, has its own network, has its own storage. Ideally, these are deployed across availability zones. So the availability zone will also isolate the worker nodes that are running in that area from things like the power. You don't really want a power issue to affect all of your availability zones. So an availability zone will usually have its own power supply. These will all be running in the same co-located geographical region. So these do need to be generally close together. And this is because when you are talking to a native HA queue manager, you're now waiting for data to be written to at least 2 of the 3 disks, not just one of them. So in a single resilient or multi-instance queue manager, you're just waiting for that data to be written once. Native HA, you need a majority of your disks to have that data to be able to tell the application that's really happened, that's really guaranteed to be persisted. Okay, so let's compare how some of those compare against each other in terms of both service and message availability. So the single resilient queue manager, as you might expect, and as I've said, is a single copy of the data. All of the applications that connect to that queue manager will be affected by the availability of that queue manager. So here we can see that the service availability and the message availability follow the pattern of each other. Once your queue manager goes, your service availability drops from 100% to 0%. Same as your message availability. Any messages which are stored on that queue manager are not available to consume by applications until that queue manager gets restarted by Kubernetes or by OpenShift. Now, whilst you may think, okay, well, I don't need to worry about my application in this case because my service availability and message availability requirements are not that high. You probably still want to worry about, well, how do my applications deal with if this queue manager isn't available? Could I have multiple single instance queue managers So if this one isn't available, I still at least have somewhere else to process new work and have somewhere to reconnect. I also maybe want to worry about the scalability. So horizontal scalability is as workload increases. If I had 3 times as many applications, do I need 3 times as many queue managers as well? A single native HA queue manager is actually very similar. The service availability and message availability of that one queue manager, again, we are talking about a single queue manager here, even though this is made up of 3 instances, this follows the pattern that the service and the message availability follow each other. But what you'll notice in this case is because native HA is tuned to very quickly detect and react to a change in availability of an active instance, it's that change in availability that allows you to shorten that window for those messages to be brought back and made available much more quickly than they would if it was just Kubernetes detecting the loss of that service and restarting the pods. So again, for applications that will really benefit from having their messages processed in a much more timely fashion, a native HA queue manager would be an improvement over a single resilient queue manager. Now, what happens when you start adding multiple ones of these? So if you say, okay, well, I want to add greater service availability by having alternate queue managers, maybe in a uniform cluster. So here we've got QMA, QMB, and QMC. It's really going to depend on your application as to the improvement that you'll see in terms of the service availability and message availability. So for tightly coupled apps, the service availability that you'll have for applications that are told that you must connect to QMA, if QMA goes down, then a third, in this case where we have the 3 queue managers, a third of your service is unavailable. Those 3 applications that can only connect to QMA will be down, albeit for a very brief time, whilst native HA gets one of the replicas to start up as an active. The service availability is still going to suffer an outage because of this tight coupling and the affinity to say these applications must connect to QMA. Even though QMB and QMC are available and applications are able to connect to those. So here still the service availability and message availability follow each other. And this is because in this instance here, these applications are still tightly coupled to the queue manager that they expect to connect to. Now, the alternate approach is where you decouple those applications to say, okay, well, that's fine. If QMA isn't available or I get a connection broken in my application from QMA, if there are alternative locations, if QMB and QMC are running, whilst they are running, I could then be able to connect and put new work through on QMB or QMC. So decoupling your applications to not have that tight affinity to any particular queue manager is a really great way of achieving that really high service availability. So whilst the messages that are stored on QMA, when QMA either goes down for maintenance or goes out for an outage, those are still locked away for that brief period of time in which it takes for QMA to recover. The service availability is still much higher percentage than the 66% you have for the message availability, and that is purely because those applications are willing to be able to reconnect. And to achieve this is where you build on some of the other features that I've mentioned, the client connection channel table, which effectively is a little telephone directory of all of the possible locations that this application could connect to, and you provide a queue manager group to say, I don't really care about which of my queue managers I do connect to. Any of the ones in this group are acceptable, and this allows you the ability to achieve that much higher service availability. Okay, so we've talked a little more around dealing with kind of unplanned failures, but there are some things that you can do to improve container availability by just kind of tuning and tweaking some of the processes. So these will apply whether you're using a single instance, a single availability queue manager, multi-instance, or indeed native HA. There's some things that you can do to really improve reduce the time at which those pods are taken down. The first is pre-pulling images. So if you are planning on rolling out a new maintenance level of MQ, then that may be several hundred megabytes that you need to pull down across the network. If you pull that image first to the nodes that it's going to be required on, then when those pods get scheduled on there to say, I need you to move to this newer image, if those images are all available on those worker nodes, that can really reduce the time at which any of your worker nodes are down for. With native HA, perhaps it's less important because you still have the quorum being able to say, in a rolling update, you just take down one at a time. So you would ideally take down replica, and then lastly the active. So your active then is able to switch over to one of the replicas very, very quickly. But certainly, you know, just as a general principle, pre-pulling those images really allows you to reduce the time at which an availability of a queue manager is down for. I talked about rolling update there. Again, if you're using OpenShift, if you're using the MQ operator, you really get some great value add there, because the MQ operator really understands the relationship between the three instances of a native HA queue manager, and so will take those down in the correct order. If you are rolling your own, if you're going with your own Kubernetes flavor and you're using the Helm charts to deploy, believe the default is it will roll out in an ordinal number. So it will take down, I think, instance 2, then instance 1, then instance 0. That may not be the optimal order, and you may end up in a situation that we call chasing the active. So if you happen to be running your active instance on instance 2 and you end instance 2 and now the active moves to instance 1, and now you end instance 1 to perform the rolling update there, and then it moves to instance 0, you then have caused the active to change 3 times. Your applications that have been disconnected get disconnected again and then again. So again, the order in which you end replicas is able to reduce that time, your recovery time. You can get back to your messages by doing it in the correct or best order. There are some other things you can do with probes and heartbeats. So whilst native HA may very, very quickly be able to determine that an active is not responsive and switch over which of the pods is running the active, it's dependent on the liveness and readiness probes that are running in Kubernetes to be able to detect that and to change which of the pods is ready. And that will mean, certainly in OpenShift, which of the routes is used to be able to redirect traffic. So the liveness and readiness probes can default to something like 5 or 10 seconds, which will mean even if native HA fails over within a sub-second, it may still be 5 seconds before your applications can be redirected to where the active has moved to. So if you really have those requirements for applications to have very, very low latency between being able to move to an active, consider changing and reducing the frequency, increasing the frequency of the readiness probes to be able to get them to be more responsive to a change in the availability. In a similar vein, on the application side, I'll talk a little around auto reconnect. So auto reconnect was added in MQ a very, very long time ago. And this was around the time at which multi-instance queue manager support was added. And by default, what will happen when your auto reconnect gets a reconnectable reason and it tries to handle this is it will go, okay, well, I'll try immediately. It might just be a network blip that means I've lost connection to the queue manager, and I'll retry immediately. And if the queue manager is not available, it will then say, okay, well, I'll start this gradual back off. So I'll go 1 second, 2 seconds, 4 seconds, 8 seconds, 16 between each retry. So it will kind of keep gradually backing this off. Now with a native HA solution, that may not be the optimal algorithm to use to be able to get your applications to very quickly reconnect to a queue manager. So it may be optimal for, again, those applications that really require this very fast ability to get back message availability, to tune that. So you can tune the recon delay for your applications to say, okay, well, maybe I want to retry immediately, and then for a couple of times I might want to retry every half a second, then every second, and then start falling back to this kind of gradual back off for something that really does look as though it's a more substantial issue that means that I can't connect to the key manager. And so, yeah, we've certainly seen that this can have really positive impacts on getting a very, very low recovery time for applications that would need it. Okay, the last section I'm going to talk around brings us on to disaster recovery. And this really, as you suggest, is the kind of fallback to the fallback. We've talked around high availability, which really deals with MQ trying to automatically detect some sort of failure and also be able to handle that itself. Disaster recovery is much more, I think, a human decision. So let's imagine that you have you have native HA deployed, and they are deployed across availability zones in a single region. And now you have some events. Maybe it's something which affects multiple availability zones. Maybe it's a flood, maybe something like that. And now that means you cannot have a majority quorum be able to allow your applications to continue messaging. So this means your business is down. And I certainly know from speaking to many customers that for certain environments, this can be very financially destructive. So at some point, it's going to be, do I fall over? Do I fail over to my backup And as I said, this is generally a human decision. So native HA, as we said, provides redundancy of effectively all the resources in an availability zone. So with the default configurations, if you have, let's say, 3 worker nodes and these are all spread across different availability zones, those nodes and instances will be deployed in such a way in anti-affinity that means they all run in all the workers will be running different pods in different availability zones. And it will mean that, again, should a single availability zone fail, then you are still able to form a majority. New work can be processed and you can carry on running the key manager. Your message and service availability has that very, very high level. There's that automatic failover, so you don't have to have a human make that decision and say, this doesn't look right. This is all automatic failover. It's all using Raft again, so it's very, very fast to be able to detect that. So whether this is a planned switch, whether this is an unplanned oops, whether it's a network partition, anything in that kind of availability zone that would cause either a degradation in the responsiveness of the active or the ability for that to process new work would allow you to very quickly be able to fail over. So what we added on top of this and in 9.4.2 is something that many customers have also been asking for, and this is cross-region replication. And this is to provide a out of region recovery. Now, what this means is, again, if I have either a true disaster, which affects multiple availability zones, something that takes out the whole area, then I need my business to become available again. So this is a human decision that you would need to make to fail over to a recovery copy. Now that recovery copy is being very regularly updated with the data from the live group, which we're calling on the left side, the live region. This is where your applications connect to. You don't have applications connect to your recovery region. This is a passive copy. Its sole purpose is to receive the data from the live region. Now, as you'll obviously notice, we've chosen to copy exactly the same topology here as well. So what does this mean? This means that the recovery region itself is also highly available. So again, each of your nodes, whether this is a planned or an unplanned failure of each of those nodes, can deal with the fact that we still want to remain very closely in contact with the live group. We want the data to be held by the recovery region to be as close as possible to where the live group is. It's async, so it's not guaranteed, but it does mean that because I have that highly available topology on the right hand side here, that should mean that the RPO is close to, or if not zero. The data is streamed across both as it is formed in quorum ahead of quorum, but is only committed into the recovery region once it's been agreed and committed back to applications. But this isn't just necessarily used for a real disaster. And we'll come on to see that in the next couple of foils and also in the demo at the end. The replication that's happening between the two groups, of course, is mandatorily TLS protected. This is because you are sending the entirety of your key manager. Every persistent message, every piece of configuration gets written to MQ logs. You are sending that over the network. You're sending this between two clusters in two different regions. You really do want to think about security. So we've mandated the requirement that you need to use your TLS to protect that traffic between these two groups. We are also using LZ4 compression. So LZ4 fast compression we added again back both to MQ channels. You can also add this onto native HA traffic. LZ4 is really fast and can be done in real time. So as the data needs to be sent across the network, but if this is a commercial cloud, then the egress traffic between these two regions may be charged by your provider. So the less number of bytes that you can send between these two clusters, obviously the cheaper for you. So we compress them. We use TLS, and we stream very closely behind the live group. That is most of the time. So there are going to be potentially different times where you may fall very far behind in your recovery group. If, for example, this is the first time you're bringing the recovery group into the configuration, it's not going to have any log data at all, and your live key manager is going to potentially have maybe gigabytes of data that it needs to send across. And so we've got this process called a group log rebase, which is used effectively to send across pretty much like an incomplete snapshot of what the key manager looks like to bring it up to a certain point in time. And so should your log data fall very far behind, this group log rebase process can be used to bring you up to date. And again, let's imagine that your recovery group was out of the picture for a period of time for whatever reason, and it needs to catch up with where stuff is today. What will happen is we will effectively park a copy of the log data that is being replicated between the groups. So there will always be a recovery point at which a recovery group can take over. So we don't just say, okay, we'll throw that data away and we'll start again, because Murphy's Law, it could be just at that point you have a real disaster on your live group, and in which case now you don't have a key manager that would be able to start in your recovery region. So in a group log rebase, we will again keep a copy of the log data. Once we have a sufficient amount of new log data to guarantee a key manager will start, we can then discard that older log data and carry on. As I say, just before we delve into the demo, this isn't just for disasters. You could use cross-region replication with other scenarios as well. So whether that's a planned outage, I don't want to imagine the number of times I've got the email saying we're having a site power down this weekend. Make sure you power off all your machines to make sure they come back up. These types of site-wide maintenance events can happen. You may have a region to move. You may have a reason to move your key manager to a different region. You may have a reason to move it to a different cloud provider. And not need to try and understand the migration tools provided by these two different cloud providers to move your data. So the one thing I haven't mentioned is in a planned failover, both of the two groups will agree that they have the same set of data before the roles are switched around. So your live and recovery groups can switch the roles around, but only once they guarantee that both have got the same set of data, which again would give you RPO 0. We'll make sure that every message, every piece of configuration that was written to your old live group is replicated before the two exchange roles. And we'll see this in the demo. Okay, so I'm going to hopefully now flip out to the demo. I will just bring up a couple of screens here. Okay, and just lastly, got that one. This one, okay. So I'll just refresh those, and I think we should be ready to go. Okay, so what I've got here is just a setup which is showing native HA and native HA cross-region replication. I have two clusters here. I have the London cluster, which is currently the live group where applications will connect. I have the San Diego group, which is set up to be the recovery group, which will just be accepting the data from London. In the session here, this is typical. In the session here, I have a run MQSC session showing that applications are told to connect to both locations. It will try London first, then it will try San Diego. You could have a load balance to do this for you, but we'll just go with the very basic solution here. QM status all. So this is a client that's connected from my local workstation, and it's connecting to an OpenShift cluster in San Jose, I think. And we can see, yeah, the instance it says is running here is on MQ1 in London. So that's where the live traffic is currently running. I will bring up my producer and consumer and hopefully not lose them this time. And I'll get these applications running. Now, these are just using the AMQS FAC and AMQS GAC samples, which are just using auto reconnect. And they're putting a message every second, consuming a message that is being put by the producer, just to show this will help us see what happens when we lose the connectivity. So I'm going to very quickly switch into my OpenShift cluster here. So the resources for London is brought together with the stateful set. So I have the 3 pods which are running, the 3 instances. The pod which is 1.1, which we saw from the MQSC session there, is running my active. So that's the kind of critically important one where applications are connected. What I'm going to do here is just show that if you delete a pod that isn't the active, again, this is maybe just an unplanned failure. I don't see any impact at all to my applications. In fact, that got restarted very, very quickly. The impact to service and message availability was absolutely minimal. In fact, nothing at all there. Now, what I'm going to do is I'm going to delete the pod for the active here and show what happens when native HA is running these very regular heartbeats. And if that's not seen by the replicas, they elect to have a new leader. So I'm going to hit delete here. We see that the connections are lost to the applications, and we should see the ready pod will switch to one of the others here. Yep, that's gone to 1.1. The probes are now going to kick in, and now my application can start putting messages again. So we had a very, very brief interruption to the service there whilst I lost the active. All of this was automatic. This is native HA being able to take over without impacting my applications in any great way. So those messages which had kind of time limited value are very quickly going to be able to get consumed again, even though they're stored on the queues there. So what I'm going to do now is going to flip to change the roles for let's flip the roles of these two groups around just to perform a planned failover. So let's have a look at key managers. So London, so we will see the role there I've put on the label is live. I'm going to change the YAML and I'm going to change the role around. So I'm going to change this from live to recovery. So the label is just kind of an aid memoir for myself to say which one was live, which one was recovery. I will change this to recovery and hit save. Okay, that's saving there. And I'm going to do the opposite in San Diego. I'm going to change this round from being recovery to live. So there we go. Let's change this from recovery to live. What we should see if I go into the resources now is the stateful set. Those pods will be rolling out. So the operators rolled this out. We now see a loss of connection as the two groups will now start negotiating between themselves to exchange data. Now, once the two groups have rolled out across all of their pods this new role, hopefully this will happen very shortly. Of course, there's always this drum roll anticipation that happens. So we've seen two go, should be this last one to go. There we go. So there we go. The applications have reconnected and we now do have these, I believe, running in different locations. So I can now connect in, display QM status. Ooh. And I can see, yep, San Diego 0 is now running my key manager. These two have swapped and there's been an exchange of data. We haven't lost any of the messages which were put to the old instance, and everything has moved over. So what I'm going to do now, just to kind of finalize the demo, is show something a bit more destructive. So let me see if I can flip back to this screen here. I'm going to, if I have time, a few minutes left, is change the YAML. I'm not going to change the YAML. We'll confirm that San Diego is live. Okay, so I'm going to delete this key manager. So I'm going to really force a disaster here. I'm going to delete this key manager. That key manager's gone. Okay, I don't have a live now. Now I'm in this awkward situation of, can I bring San Diego back up? Or if I go to the YAML, I can put the live back to London. And what I need to do here is I need to say San Diego, unfortunately, is gone. Okay, I don't want you to exchange the data with San Diego and both agree that you've got that. I just want you to go alone. I want you to start up as the live and not wait for San Diego to confirm you have all the right data. So this is an unplanned failover. I wasn't expecting San Diego to be unavailable, and now London's going to become my, hopefully, if the demo goes to plan, should become my.
Yeah, just a couple of minutes, John.
Thanks, Ray. So hopefully we should see the change in the configuration ripple through here. There we go. Fantastic. You know, I've had the, whereas actually, as we can see here, we don't need all three to have that. The container is still creating on the third instance. I just need a majority of the group. I can have a redundancy of one of these not running to be able to perform the failover.
All right. Well, John, it's a
Okay.
brave man that does a live demo. So congrats. All right, guys, we're right here at the top of the hour. So we're going to be transitioning over to what's new in event endpoint management. You know the drill. Please do the survey, take the poll, and we will see you over on the next session here in just 5 minutes. Thanks, John. Great job.